Hey grade 12s, today what we're going to do is we're going to look at solving Ka and Kb problems, and we're going to start by looking at weak acids and weak bases. There's two types of problems we're going to look at today. We're going to look at calculating the dissociation constant, and that's what we're going to start off with. So let's lead off with this question right here. A weak base, ammonia, has a concentration of 0.75 moles per liter at equilibrium. The hydroxide ion concentration at equilibrium is 1 times 10 to the negative 4 moles per liter. Find the constant Kb. So let's write out the chemical equation. It's going to be ammonia plus water gives us the ammonium ion and the hydroxide ion. So we know right off the hop that there's a concentration of 0.75 here. There's nothing here, nothing here. And this is the concentration at equilibrium of the hydroxide ion. So that's being added. So it's going to be plus 1 times 10 to the negative 4 plus 1 times 10 to the negative 4. And because the molar ratios are all 1 to 1 to 1 to 1, we're going to go minus 1 times 10 to the negative 4. That's being taken away from the 0.75. And what is that going to give us? Well, it's going to give us 0.00, oopsies, my bad. It's going to give us 0.7499, and this is going to be 1 times 10 to the negative 4, 1 times 10 to the negative 4. And now, in order to figure out the value of Kb, we know that Kb is going to be the product of the concentration of the products. So that's going to be 1 times 10 to the negative 4 times 1 times 10 to the negative 4 all over the concentration of ammonia, which is 0.7499. So we're going to go ahead and do that calculation here. And so let me just type it into my calculator here. So we go 10 to the negative 4. And we're going to square it. Then we're going to divide by 0.7499. And that's going to give us a Kb value of 1.33 times 10 to the negative 8. Okay, so that is the Kb value for that situation. Okay. All right, moving on to the next example. We have a 0.10 molar solution of acetic acid. It's only partly ionized. Okay, so at equilibrium, the hydronium ion concentration is 1.3 times 10 to the negative 3 moles per liter. What's the acid dissociation constant, which is Ka. So again, we're going to start by writing out the chemical equation. So we're going to start off with acetic acid, which is going to be HC2H3O2 plus H2O, and that's going to give us H3O plus, the hydronium ion, and the acetate ion, which would be C2H3O2 minus. Molar ratios are all 1 to 1 to 1 to 1. So we're going to look at the number of moles, or rather the molarity or the concentration, We start off with a molarity of 0.1 here, that's 0, 0. And then what we see for the next line is that the molarity increases for hydronium by 1.3 times 10 to the negative 3. So it's also going to increase by the same amount here. But that also means it's going to decrease by that same amount for the acetic acid. And then we have to find the final concentrations. And the final concentrations for the products are really straightforward. It's just 1.3 times 10 to the negative 3. But for the acetic acid, it's going to be 0.987, and the units for all of those are moles per liter. Now, to figure out Ka can be found by multiplying the concentrations of the products. Since they're the same, we can just square it and then divide by 0.987. So when we do that, we're going to get a constant value of 1.712 times 10 to the negative 5. And there's no units for the value of Ka. Okay? All right. And with that, we're going to move on to the next example. So here's the next example. HA is a weak acid. It has a Ka of 7.3 times 10 to the negative 8. What's the concentration of all species if the initial concentration of HA is 0.5 moles per liter? So what would the chemical equation look like to start with? Well, it would be HA plus H2O, which gives us the hydronium ion and the negative ion as well. And what we know is that the initial concentration of the acid is 0.5 molar. That's 0, that's 0. We also know that what we can do is we can go ahead and then see what the change would be. We don't know what the change is, but what we can do is we can call the change x. And 0 plus x is going to be x. And the concentration of the weak acid will be 0.5 minus whatever x is. Okay? And once we have that, well, we can set up our Ka expression. And our Ka expression should be Ka equals x times x all over 0.5 minus x. We know the value of Ka that's provided to us in the question. It's 7.3 times 10 to the negative 8. On the right side, we have x squared over 0.5 minus x. Now, we're going to use the same idea as when we did chemical equilibrium questions. 0.5 minus x is very close to 0.5. So, in that expression only, we're going to ignore x. And that allows us to rewrite this as 7.3 times 10 to the negative 8 equals x squared over 0.5. If we multiply 0.5 by the value of Ka, we're going to get 3.65 times 10 to the negative 8 equals x squared. Then we just have to take the square root of 3.65 times 10 to the negative 8, and x equals 1.91 times 10 to the negative 4. And that is a concentration, so it is in moles per liter. So that's the value of x. And keep in mind what the question was asking us. The question was, what is the concentration of all species? So now that we figure out what x is, we can go ahead and answer that question. So, the ions are super easy because they are just x. So that is going to be just 1.91 times 10 to the negative 4 moles per liter, and that is for both of them. And for the concentration of the weak acid, we'll have to figure out what 0.5 minus 1.91 times 10 to the negative 4 is. When you go ahead and do that, you're going to get 0.49981, just like that. And that's also in moles per liter. So the question asked us what was the concentration of all species. Well, the concentration of the weak acid is that. The concentration of the hydronium ion and the concentration of the other ion in the products are the same. It's the 1.91 times 10 to the negative 4, which corresponds with that x value that we found. Okay, so there was a little bit more of that question because we had to do a little bit of arithmetic. But once we understand this question, it'll help us do similar questions when you get your practice assignment. Okay. Now we're going to talk about that percent dissociation. Acids and bases can be described in terms of being strong or weak, concentration, and the degree of dissociation. The acid and base dissociation constants represent the degree of dissociation or ionization achieved by the acid or base. Another way to describe the amount of dissociation is by percent dissociation. Now, percentage dissociation is kind of like just figuring out percent. So it's, if you understand how you do percent, then it's going to be fairly straightforward. The percent dissociation is just going to be the concentration of the dissociated species divided by the original concentration of the acid or base. So basically, for an acid, it would be the hydronium ion concentration divided by the concentration of that acid times 100. And for a base, it'd be the hydroxide ion concentration divided by the concentration of the base times 100. So fairly straightforward there. In order to figure out what the percent dissociation is, and calculations are fairly straightforward. And it's using things that we're already familiar with doing. So let's go ahead and do an example here. Calculate the percent dissociation of a 0.1 molar solution of formic acid if the hydronium ion concentration is 4.21 times 10 to the negative 3 moles per liter. So straight up then, this calculation is fairly straightforward. It's just going to be It's just going to be 4.21 times 10 to the negative 3 divided by 0.1 times 100. So if you go ahead and you do that, what you're going to find is the percent dissociation is 4.21%. That's the percent that dissociates. Okay. So we just divide the two concentrations, multiply by 100, and that's all she wrote. Let's try another example. Calculate the Kb of the hydrogen phosphate ion if a 0.25 molar solution of sodium hydrogen phosphate is dissociated to 0.08%. All right, so we're going to take a look at the hydrogen phosphate ion first. We're going to add water to it. And that's going to give us that. All right, so we know that the hydrogen phosphate ion has an initial concentration of 0.25 molar. And we also know that there is a dissociation of 0.08%. So we need to use that in order to help us here. Okay, so how is that going to help us? Well, what we know is this concentration here is going to be 0.08% of 0.25. So in order to figure that out, we're going to go 0.08 over 100 times 0.25. And we're going to get 2 times 10 to the negative 4. And that'll also match the concentration over here, of course. And then to figure out the concentration of the hydrogen phosphate ion, it's going to be 0.25 minus 2 times 10 to the negative 4, which is going to be 0.2498. Okay, and that's also molar, molar, and molar. All right, now what we can do, now that we have the concentration of all those species, we can figure out the Kb value. Kb is going to be 2 times 10 to the negative 4, and there's 2 of them, so we can square it, and we're going to divide by 0.2498, and when the dust settles, we get 1.601 times 10 to the negative 7 as the Kb value. So we got a couple more examples here, and here's the next one. It talks about pH, Ka, and Kb. What's the pH of a 0.1 molar solution of the imaginary acid HA if its Ka is 4 times 10 to the negative 9? So let's take a look at what the chemical reaction would look like. We've got our acid, we're going to add it to water, and we're going to get the hydronium ion, and we're going to get A minus. Okay, so here's what we know. Initial concentrations. Well, the initial concentration is going to be 0.1 molar. That's going to be nothing. That's going to be nothing. We know that here it's going to be X and X, and we're going to have 0.1 minus X here. We don't know what X is, but that's what we know. So we have to use these algebraic expressions with the given Ka in an effort to find X. Because ultimately, once we find X, what we're going to do is we're going to be able to go ahead and find the pH after we know the concentration of the hydronium ion. Okay? So, let's get to it. So, we know that Ka is X times X over 0.1 minus X. We already know the Ka value. It's 4 times 10 to the negative 9. We have X squared here. We could ignore the X in the denominator, so it's just going to be 0.1 there. Doing some multiplication, we're going to get 4 times 10 to the negative 10 equals X squared, which means we could take the square root to figure out what X is, and we're going to get 2 times 10 to the negative 5. That's the concentration that we get for the value of X. And more importantly, that gives us the hydronium ion concentration. Because yes, it's also the value of A minus, and yes, it can also help us find the concentration, the initial or the final concentration of the acid, but we're not looking for those things. We just need to use the hydronium ion concentration to find the pH, because we know that the pH is the negative log of the hydronium ion concentration. So in other words, we're going to figure out the negative log of 2 times 10 to the negative 5. And when we do that, what we're going to find is that the answer is 4.69. So the pH of the imaginary acid is 4.69. So we use the provided Ka value, the provided initial concentration of the acid. We came up with an algebraic expression to represent the equilibrium concentrations of H3O plus the A minus, and we threw those into the Ka expression to solve for X. X, of course, gave us the hydronium ion concentration, and since we knew the hydronium ion concentration, then we could pivot and we could calculate the pH. Okay? So there are a few things going on there and a few steps you need to follow, but once you see what those steps are, it's not so bad. All right, now we've got one final example. The pH of a 0.2 molar solution of carbonate ions is 10.75. What is the Kb of carbonate ions? So what we're going to do is we're going to go ahead and we're going to write out a chemical equation. A chemical equation, of course, is going to be the carbonate ion plus water, and we're going to donate a hydrogen atom, so we get HCO3 minus, and we'll also get our nice OH minus too, our hydroxide ion. We also know that initially there's nothing of this and nothing of this, and there's also 0.2 molar of the carbonate ions. Now, going forward from there, what do we need to know? Well, what we need to know is we need to be able to find the hydroxide ion concentration. And what we're told is that the pH is 10.75. Okay, the pH is 10.75. So what we could do then is we could find the pOH. The pOH. The pOH is going to be 14 minus 10.75. The pOH is going to be 3.25. Once we have the pOH, we also know that the hydroxide ion concentration can be found from 10 to the negative pOH. So that's 10 to the negative 3.25. So let's go ahead and figure out what that is. So if we figure out what 10 to the negative 3.25 is, what we get is 5.62 times 10 to the negative 4. That represents the hydroxide ion concentration. So because that represents the hydroxide ion concentration, that means that that can become the at equilibrium concentration of the hydroxide ions. So we could put 5.62 times 10 to the negative 4 moles per liter here. Of course, we also know that the same thing is going to be here because of the 1-to-1 molar ratio. And the same thing is going to be subtracted from the initial concentration of the carbonate ions. So when we take 0.2 and we subtract 5.62 times 10 to the negative 4, what we're going to get is we're going to get 0.1994376 moles per liter. And we're going to use that as well as the other two concentrations that are written in green to help us figure out the value of Kb. And of course, Kb is the product of the products, their concentrations, of course. So that's going to be 5.62 times 10 to the negative 4 squared, because we're multiplying them together, all divided by the concentration of the carbonate ions later on, which is 0.1994376. So the value for Kb is 1.58 times 10 to the negative 6. That's the value of Kb. So in this question, what we had to do is we had to write that chemical equation, and then that led us to doing this work in red here. We would use the given pH to help us figure out the pOH. And once we had the pOH, we were able to find the hydroxide ion concentration by going 10 to the negative pOH, and that gave us 5.62 times 10 to the negative 4. And I see I'm missing a unit here that should be moles per liter. And that number, of course, transferred over to the concentration of hydroxide ions. And of course, it's the same thing here because of the 1-to-1 molar ratio for the products. And that also was the same number that we subtracted from 0.2 for the final concentration of the carbonate ions. And then we use those concentrations written in green to help us find the value of Kb, which was 1.58 times 10 to the negative 6.